Everything you need to know about Zener diodes. Before we had all the modern regulators and protection ICs, engineers relied on simple components to keep voltages under control, such as the Zener diode. It's used everywhere, stabilizing voltages, clamping spikes, protecting microcontrollers, and most people don't even realize it's there. What is a Zener diode and how does it work? Hopefully you have all watched our previous video on standard diodes. If you haven't, you can view it here. But essentially, a Zener diode is a special type of diode designed to operate in reverse bias breakdown safely and repeatedly. A normal diode is meant to block reverse voltage, but a Zener diode is designed to break down specific reverse voltage and hold that voltage nearly constant. That specific voltage is called the Zener voltage, and it's usually written as VZ. On schematics, a Zener diode looks like a regular diode, except the cathode line is kinked or angled, showing it's designed to regulate voltage in reverse bias. We can visualize how a Zener works this by using a basic circuit. We have a voltage source and we connect a Zener diode in reverse bias. The cathode goes to the positive side and the anode goes to ground. At first, when the diode is reverse biased at low voltages, the current is extremely small, limited pretty much only to leakage through the junction. As the reverse voltage increases, the electric field across the junction strengthens until a critical point is reached where the diode enters reverse breakdown. This point is known as the breakdown voltage, or more specifically, the Zener voltage. Once the diode reaches this region, the reverse current increases sharply, but the voltage across the Zener diode remains nearly constant. That ability to maintain a fixed voltage even as current varies is exactly what makes Zener diodes useful as voltage regulators and voltage reference devices. The clearest way to see this behavior is by looking at the Zener diode current voltage characteristic, or IV curve. The Zener diode IV curve. If we look at the Zener diode IV curve in the forward bias direction, the IV characteristic looks just like that of a standard silicon diode. The current remains very small at low voltages and then increases sharply once the forward voltage exceeds the junction's turn-on threshold. In reverse bias, however, the behavior is very different. It stays almost flat until the breakdown region. At the breakdown knee, the reverse current increases sharply, while the voltage across the diode remains pretty much constant as the Zener voltage. This near horizontal region of the IV curve is what people are referring to when they say a Zener diode clamps the voltage. Essentially, the Zener diode is acting as a voltage stabilizer, holding the output voltage steady despite changes in current. If you're enjoying this deep dive into how Zener diodes work, make sure you hit that subscribe button and give us a thumbs up. You can also check out our online store for engineering-themed gear and tools that help support the channel. Every purchase genuinely helps us keep making high-quality content. And if you want to take things a step further, consider becoming an Engineeringness member. You'll get early access to new videos, behind-the-scenes content showing how we animate and build these breakdowns, and access to our member-only chat rooms where we talk about all things engineering. The anatomy of a Zener diode. Now let's take a look inside a Zener diode and see what actually makes it different from a standard diode. At its core is still a semiconductor die with a PN junction, but in a Zener diode, that junction is deliberately designed with specific doping levels. This heavy and precise doping determines how thin the depletion region is and sets the exact Zener breakdown voltage of the device. Attached to the semiconductor die are tiny metal contacts and bond wires, which provide the electrical connection between the junction and the external circuit, allowing current to flow both in forward conduction and in controlled reverse breakdown. Surrounding the die is the package and encapsulation, which protects the junction from mechanical damage, moisture, and contamination, while also helping to dissipate heat generated when the diode operates in breakdown. Zener diodes are commonly housed in small glass or plastic packages, often marked with a stripe to clearly indicate the cathode. Finally, the leads or terminals extend from the package, providing a way to mount the Zener diode onto a circuit board and connect it into a circuit where it can regulate, clamp, or protect voltage levels. Why does it break down? Zener effect versus avalanche effect. Reverse breakdown in a Zener diode doesn't happen for just one reason. There are actually two distinct physical mechanisms that can be responsible. Let's start by firstly discussing the Zener breakdown or tunneling. Zener breakdown is dominant at lower breakdown voltages, usually below about 5 to 6 volts. In these diodes, the PN junction is heavily doped, which results in an extremely thin depletion region. When a reverse voltage is applied, this thin depletion region produces a very strong electric field across the junction. At a critical field strength, electrons are able to quantum tunnel through the energy barrier directly from the valence band to the conduction band due to the wave nature of the electrons. This tunneling process is known as the Zener effect, and it causes a rapid increase in reverse current while the voltage remains nearly constant. Secondly, there is avalanche breakdown. At higher breakdown voltages, typically above 5.6 volts, a different mechanism becomes dominant, known as the avalanche breakdown. In this case, the depletion region is wider and the electric field accelerates charge carriers to high energies. These energetic carriers collide with atoms in the lattice, knocking loose additional electrons. Those newly freed carriers are then accelerated as well, creating a chain reaction. This is called an avalanche, and it leads to a sharp rise in reverse current. Why 5.6 volt Zeners are special? Around 5.6 volts, both Zener tunneling and avalanche breakdown can occur simultaneously. Because the two mechanisms have opposing temperature coefficients, their temperature effects can partially cancel out. As a result, Zener diodes with breakdown voltages near 5.6 volts tend to be especially temperature stable, which is why they're so commonly used in practical circuit designs. Zener diode as a voltage regulator. Now let's look at the most common practical application of a Zener diode, which is when it is used as a voltage regulator. We start with an input supply voltage, Vin, feeding a series current limiting resistor, Rs. The Zener diode is then connected from the output node to the ground in reverse bias, and the load is connected in parallel with the Zener diode. The regulated output is taken directly across the Zener diode. When the Zener diode is operating in its breakdown region, the output voltage is approximately equal to the Zener voltage. So we can say Vout roughly equals Vz. The series resistor plays a really important role here. It limits the current supplied to both the load and the Zener diode. Without this resistor, once breakdown occurs, the Zener diode would attempt to draw excessive current from the supply and would quickly overheat and fail. The current flowing through the series resistor is given by the equation Is equals Vin minus Vz over Rs. This resistor current then splits between the Zener diode and the load, so we can say Is equals Iz plus IL. This current sharing behavior is what allows voltage regulation. If the load current increases, more current is drawn by the load and the Zener current decreases. If the load current decreases, less current is drawn by the load and the Zener current increases. As long as the Zener diode remains in its breakdown region and within its power rating, it automatically adjusts its current to maintain a nearly constant output voltage. The primary limiting factor of Zener diodes is Zener power dissipation. A Zener diode regulates voltage by operating in reverse breakdown, which means any excess energy from the supply is dissipated within the diode itself, primarily as heat. The power dissipated in the Zener diode is given by Pz equals Vz multiplied by Iz. As the Zener current increases, the power dissipation rises proportionally. If this power exceeds the diode's rated limit, the junction temperature increases beyond safe operating conditions, leading to thermal runaway and eventual device failure. For this reason, Zener diodes are specified with maximum power ratings. When designing a Zener-based regulator or clamp circuit, it is really important to evaluate the worst-case Zener current and ensure that the resulting power dissipation remains well below the maximum rating specified in the datasheet. As with any component, Zener diodes have drawbacks. They're simple and cheap, but they're not the best option for everything. Here are some more Zener diode limitations. They waste power. Because regulation happens by burning excess energy as heat, Zeners are inefficient for higher current loads. They're not ideal for powering loads directly. If you want a stable supply rail for something drawing real current, you'll usually use an LDO or a switching regulator. They can be noisy, especially lower voltage Zeners, because tunneling breakdown can introduce noise. Temperature drift. Depending on the Zener voltage, the breakdown voltage can change slightly with temperature. If you enjoyed this video and learned something new, don't forget to subscribe to Engineering This. Give us a thumbs up, check out our online store for unique engineering merch, and consider becoming a member to get early access to all our videos and behind-the-scenes animations. Thanks for watching. See you in the next one.